Jai Hind students, myself Dr. Meenakshi Sinha. I am assistant professor in Ajay Kumar Garg Engineering College, Ghaziabad. Today I am delivering the topic for BTech first year students for Engineering Mathematics 1 course with subject code BAS 103T. Today I am taking the module 3, which is the differential calculus second, and the topic which I cover in this video lecture is Jacobian. In Jacobian, we are discussing about the properties of Jacobian of implicit function and functional dependency of Jacobian. So, first of all, what is the meaning of Jacobian? So, if you look at the introduction of Jacobian, so by definition, if u equal to uxy, v equal to vxy be two functions of x and y, where x and y are independent variables, then the value of this Jacobian is known as Jacobian of uv with respect to x and y. Yeah. So, what is the meaning? That u is the function of two independent variables x and y, v is also the function of two independent variables x and y. Then we find out the Jacobian of uv with respect to x and y, and Jacobian is nothing but this type of determinant. How we solve this determinant? First we take this u, take the partial derivative of u with respect to x and with respect to y both, and put it in the first column. So, del u by del x, del u by del y are kept in the first row, Then take the second variable y, take its partial derivative with respect to x and y both. So, in the second row we have del v by del x and del v by del y. Put it in the determinant form, and solving this determinant gives you the value of the Jacobian. The Jacobian is denoted by the symbol del uv by del xy or JUV. JUV is nothing but del u by del x, del u by del y, del v by del x and del v by del y, this del uv. So, this is the definition of Jacobian. So, Jacobian is nothing but finding the value of partial derivatives of dependent variables with respect to independent variables and putting in the determinant form. So, it is very important in transformation of variables from one coordinate system to another coordinate system, and Jacobian is also used to calculate the area and volume integrals. This one. In the previous slide, we have just seen that how to write the Jacobian of function of two variables. So, it can be extended for three variables also. So, Jacobian for three variable function means if u is the function of x, y, z, v is also the function of x, y, z, w is also the function of three variables x, y, z, then the Jacobian of u, v, w with respect to x, y, z. What we do? In the first column, we take this u, take the partial derivative of u with respect to x, y and z, del u by del x, del u by del y and del u by del z. In the second, we have the second variable is v. So, second row is del v by del x, del v by del y and del v by del z. Third independent variable is w. Take its partial derivative with respect to x, y, z, put it in the third row. So, this is the Jacobian of three variables, this one. So, similarly, we can extend this definition for n variables. So, if u1, u2, un are n number of dependent variables which are the function of n independent variables x1, x2, xn, then Jacobian of u1, u2, un with respect to x1, x2, xn is given by putting each values like this in the form of determinant. So, this is the definition of Jacobian. So, look at one of the example of this Jacobian. Means question says find Jacobian of uvw with respect to xyz. Means here uvw are taken as dependent variables and xyz are taken as independent variables from the following relations. Relation given is u equal to x plus 2y plus z, v equal to x plus 2y plus 3z and w equal to 2x plus 3y plus 5z. This is the value uvw. So, in the solution, if we start with, we have given the values of u, v and w here as a function of x, y, z. So, we start calculating this Jacobian of u, v, w with respect to x, y, z. So, look at, by definition, if I write this in the determinant form, so what I write in the first row, I take this first dependent variable u and take its partial with respect to all the three independent variables and put it in the first row. What we get? In the first row we have del u by del x, the first element, del u by del y, the second element, and del u by del z as the third element. In the second row, take the second dependent variable v and take its partial with respect to three variables x, y, z. So, second elements are del v by del x, this is del v by del y, and the third one is del v by del z. Third dependent variable is w, take its partial again, writing in the third row, it's del w by del x, del w by del y, and del w by del z, like this. Now, after writing the definition, just we need to find out all these partials for this given relation. So, finding the partials, del u by del x, from here it's clear that del u by del x will become equal to 1, del u by del y is nothing but 2, del u by del z is 1, partial derivatives. Similar, the second row, del v by del x is 1, del v by del y is 2, and del v by del w is del z is 3. In the third row, del w by del x is 2, del w by del y 3, and next is 5. So, this is the determinant which gives you the value of Jacobian. Now, you all know how to solve a determinant. So, suppose we are expanding this determinant by the first column. If I expand it by the first column, taking this 1 multiplied by 5 2s are 10 minus 3 3s are 9 minus the second element is 1 here, so minus 1 into, leaving this row and this column, we get 5 2s are 10 minus 3, this one, and plus the last element is 2 over here, leaving this column and this row, we get 3 2s are 6 minus 2, like this. Now, solving this value, 10 minus 9 is nothing but 8, 10 minus 3 is nothing but 7, so this is minus 7, 6 minus 2 is 4, and 4 2s are 8, so plus 8. So, this we get the value something like, what we get, 8 minus 7 is nothing but this one. Look at the calculation, we have 1 2 1, just a minute, 1 2 3 and 2 3 and 5, we are doing like this, clear. So, when we have expanded, it's 1, 5 2s are 10 minus 3 3s are 9, okay, 10 minus 9 is only, sorry, 1, this is 1, nothing but. And solving this value, what we get, 8 plus 1 is 9 minus 7 is nothing but 2. So, the final answer of this Jacobian is nothing but we are getting the value 2 over here, clear. So, this is how we find out the Jacobian for a given relation, clear. Look at one more example, what we have here. We have here y1 equal to, I write it again, y1 equal to x2 x3 by x1, y2 given as x3 x1 by x2, y3 given as x1 x2 by x3. You have to find out the Jacobian of y1, y2, y3. What's the meaning? That y1, y2, y3 here are dependent variables, x1, x2, x3 here are independent variables. So, you have to find out the Jacobian y1, y2, y3 with respect to x1, x2 and x3. So, first step is to find out all the partial derivatives over here. So, just look at what are the partials over here. First, we find out starting with the value del y1 by del x1. Starting with this y1, del y1 by del x1, take the partial with respect to x1, what we get, look at. This x2, x3 remains same, and for 1 by x1, the partial derivative of 1 by x1 with respect to x1 is nothing but minus x1 square, like this, clear. Next is del y2 by del x1, del y2 by del x1 with respect to x1, I write its derivative is 1, it's left with x3 by x2. Del y3 by del x1, y3 partial with respect to x1 is nothing but x2 by x3, this one. Del y1 by del x2, del y1 by del x2 is nothing but x3 by x1, this one. Del y2 by del x2, del y2 by del x2 is nothing but minus x3 x1 divided by x2 square, and del y3 by del x2 nothing but x1 by x3. Similar, we can find out the other partial derivatives by using this. Now, what is the next step? Next step, we put this partials over here in the definition of Jacobian. So, we are taking here the definition Jacobian, y1 partial with respect to x1, x2, x3 in the first row, del y2 by del x1, del y2 by del x2 in the second row, and y3 partial with respect to 3 variables in the third row. Now putting these partials over here, which we have calculated. So this is minus x2 x3 by x1 square, x3 by x1, x2 by x1, x3 by x2 minus x3 x1 by x2 square, x1 by x2, and x2 by x3, x1 by x3 minus x1 x2 by x3 square. Now we need to solve this determinant. So how we solve it? We know that we can take common from any of the row or any of the column in solving a determinant. So look at what we take common outside over here. So look at in the first row. In the first row, we are going to take 1 by x1 square common outside. From the second row, I am taking 1 by x2 square common outside. From the third row, I am taking 1 by x3 square common outside. Now look at what we left inside the determinant. So when I take these commons over here, 1 by x1 square is common. So I left with the value minus x2 x3 inside the bracket. 1 by x1 square is common. So one of the x1 is multiplied over here. I left with the value x1 x3. Similar, 1 by x1 square is common. So I left with the value x1 x2 like this. From here I taken 1 by x2 square common, so this will become nothing but x2 x3. This is minus x3 x1, and from here we get x1 x2, thing like this. x3 square is common, so I get over here x2 x3, x1 x3, and minus x1 x2 like this. Again we check that what we take common from now these three terms. If I look at now this, so this 1 by x1 square, x2 square, x3 square is already over here. If I look at now the rows, from the first row if I check this x2, x3, x1, x3 and sorry from the first column, look at x2, x3, x2, x3, x2, x3. So from the first column I am taking x2, x3 common outside. From the second column, it's x1, x3, x1, x3, x. So from the second column, we are taking x1, x3 common outside. From the third column, it's x1, x2, the values are same. So we take x1, x2 common outside, like this one. So what we left with inside the determinant? Taking this common, we left with minus 1, 1, 1. This is 1, minus 1, 1, and this is 1, 1, minus 1. And in the numerator, what we left with? We have the x1 square, x2 square, and x3 square, which will cancel out from denominator value. So this will cancel out, and finally look at this, we left with the value minus 1, 1, 1. We have 1 minus 1, 1 and 1, 1 minus 1. So solving this determinant, this will cancel out both the values, and solving this determinant, look at what we get. We get the value 0 plus 2 plus 2, which is equal to 4. So this 4 is the value of this Jacobian of y1, y2, y3 with respect to x1, x2, x3. So this is, we have here used the basic definition of Jacobian, that how we able to find out the Jacobians over here. So now next slide, coming to some of the properties of Jacobian, look at the first property. The first property says that if u equal to function of x and y and v equal to is also the function of x and y, be two functions of x and y where x and y are independent variables, then Jacobian of uv is del uv by del xy. This is denoted by the symbol j, and if Jacobian of xy with respect to uv is denoted by the symbol j dash, then the first property says that j into j dash must be always equal to 1. Then j into j dash must be always equal to 1. Clear? So that is Jacobian of uv with respect to xy multiplied by Jacobian of xy with respect to uv, its product is always 1. So this is the first important property of Jacobian. The second property of Jacobian is known as chain rule. So what is chain rule of Jacobian? It says that if uv are the functions of r and s are the functions of x and y, and I need to find out the Jacobian of uv with respect to xy, then by chain rule what it said? It says that Jacobian of uv with respect to xy is the product of Jacobian of uv with respect to r and s. Jacobian of uv with respect to r and s, and Jacobian of r and s with respect to x and y. So we move like this. So if I need to find Jacobian of uv with respect to xy, it's the product of two Jacobians. The first one is the Jacobian of uv with respect to rs multiplied by the Jacobian of rs with respect to x and y. So this property of Jacobian is known as the chain rule of Jacobian. So they are the two important properties of Jacobian. Now look at some of the examples based on these properties. So the first example we are taking over here, that if x is given as r cos theta and y equal to r sin theta, then find the Jacobian of xy and Jacobian of r theta. First we start finding the Jacobian of xy. How? Because x and y here are given as the dependent variables and r and theta are the independent variables. So we start the solution over here. If I look at over here, x is the value r cos theta and y is the value r sin theta. Look at, if I start finding the Jacobian of xy with respect to r theta, so what we get? By our definition, this is nothing but del x by del r, del x by del theta. Taking the second dependent variable, we have del y by del r and del y by del theta. Finding next these partial derivatives and put it over here. So look at what we get. This is the definition of Jacobian. Next we put the values over here. Look at del x by del r. If I take the partial of x with respect to r, what I left with this is nothing but cos theta. This one. Del x by del theta next, the partial of x with respect to theta. The partial derivative of cos theta is nothing but minus sin theta. So this is minus r sin theta. Next is del y by del r. Del y by del r is nothing but sin theta. This one. And del v by this del y by del theta. Del y by del theta is nothing but derivative of sin theta is cos theta. So this is r cos theta. So when I start solving this determinant, what we get? I get something like r into cos squared theta plus sin squared theta, which we know that this is equal to 1. So we get the value of this Jacobian as r. So this is equal to r. Now what we need to find? We need to find another Jacobian of r theta with respect to xy. So what we apply? Here I apply the first property of Jacobian. I know that Jacobian of xy with respect to r theta multiplied by Jacobian of r theta with respect to xy. By the first property, this is always equal to 1. This Jacobian, I have already calculated, its value is r. So the value of this Jacobian will nothing but equal to 1 upon r. So by the property j into j dash is 1. So j dash will become equal to 1 upon j. J we have already calculated as r. So its value will become equal to 1 by r. So j dash comes out to be equal to 1 by r. That's how we use the first property over here. Look at one more example for the second property. What this is, you are provided that u equal to xy, v equal to x minus y, x equal to r cos theta and y equal to r sin theta. Then find out the Jacobian of uv. If you look at in these relation, what is given to you? We are provided that u here and v are the functions of x and y, and x and y are given further functions of r and theta. What we need to find? We need to find the Jacobian of u and v with respect to r and theta. This Jacobian we need to find. This one. Yeah. So here we apply the chain rule of Jacobian. By the chain rule, what we say? That Jacobian of uv with respect to r theta. Like we move one by one. It's equal to the Jacobian of uv with respect to xy, and xy are further function of r theta. So multiplied by Jacobian of xy with respect to r theta. This one. So what we do? Individually we find out this Jacobian and this Jacobian. We take their product. We get the Jacobian of uv with respect to r theta. This one. Clear? So what we have started writing by definition, del u v by del xy is this, del u by del x, del u by del y, del v by del x, del v by del y. Del xy by del r theta is del x by del r, del x by del theta in the first row, del y by del r and del y by del theta in the second row. Next we start finding their partial derivatives using these relations. If I use the relation del x by del u, is clear that del u by del x is nothing but y, del u by del y is x, yeah. Del v by del x is plus 1 and del v by del y is minus 1. Similar, the second relation, del x by del r is cos theta, del x by del theta is minus r sin theta, del y by del r is sin theta and del y by del theta is r cos theta. Now solving this, look at what we get. If I solve now this determinant, look at what I get. Here I get minus y minus x. I write like this, minus y minus x. This is from the first determinant. In the second determinant, we have just recently solved it in the last question. What I get r cos square theta plus r sin square theta, which will give me the value r. Taking minus sign common out here, this is nothing but minus r into x plus y. So this is the second result, minus r into x plus y. And what we do in the last result, we just put the value of x and y over here in terms of r and theta. So when we put x equal to, look at, minus r, x is equal to r cos theta and y is equal to r sin theta. Taking r common from here, so this will become minus r squared sin theta plus cos theta. This is the final value of Jacobian del u v by del r theta. And this question we have solved by using the second property of Jacobian, which is the chain rule. So this is also very important property of Jacobian, means this gives me the indirect Jacobian, means the Jacobian of uv with respect to r theta by moving one by one like this. Okay. So next we are coming to an important topic of Jacobian, which is called the Jacobian of implicit function. What is the meaning implicit function? First of all, implicit function means that if x and y are connected from such type of relation from which we can't write y either in terms of x or x as a function of y. Like for example, if I write down a relation, I write down like this, x cube plus y cube is plus u cube plus v cube equal to 0. If I ask you to write x in terms of u and v, so it's not possible to write over here x as a function of u and v. Or if I ask you that write u as a function of x and y, that's also not. So I say that this relation is an implicit relation. So implicit. So next topic we have the Jacobian of implicit. That's how we, means if I not able to write the dependent variable in terms of independent variables, then how we find out the Jacobian of such functions. So if u1, u2, u3 are the functions of x1, x2, x3, and if they are connected themselves by a relation, which type of relation? Relation of the type like f1, f2, f3 are the notation of these three relations. f1 is the function of u1, u2, u3, x1, x2, x3 equal to 0. f2 is also the function of all these 6 variables. f3 is also the function of all these 6 variables. And these three are must be the implicit. Means implicit means that we not able to identify that out of these 6 variables, which are the dependent variables, which are the independent variables. So in this case, how we find out the Jacobian? The formula for finding the Jacobian is the Jacobian of u1, u2, u3 with respect to x1, x2, x3 is given by minus 1 to the power 3. Jacobian of f1, f2, f3 with respect to x1, x2, x3 divided by Jacobian of f1, f2, f3 with respect to u1, u2, u3. Means in this question we have to find out 2 Jacobians. First we have to find the Jacobian of these f1, f2, f3 with respect to x1, x2, x3. Next we have to find the Jacobian of f1, f2, f3 with respect to u1, u2, u3. Just take their division, minus 1 to the power 3. This gives me the value for the Jacobian of u1, u2, u3 with respect to x1, x2, x3 like this. So this is the formula how we find out the Jacobian for function of 3 variables. We can expand this formula for n number of variables also. So if we need to find the Jacobian of u1, u2, u3 with respect to x1, x2, x3, xn, then this Jacobian, the formula changes, that this will become minus 1 to the power n over here, because here we have n variables. Jacobian f1, f2, fn with respect to first x1, x2, xn and divided by f1, f2, fn divided by u1, u2, un, like this one. Clear? So this is the formula for finding the Jacobian of implicit function, in which we have n variables, n number of dependent variables and n number of independent variables, like this one. So this is also very important topic, that how we find out the Jacobian of an implicit function. Clear? So looking at one of the example for this, look at, we are provided that if u cube plus v cube plus w cube is equal to x plus y plus z, u square plus v square plus w square is equal to x cube plus y cube plus z cube, and u plus v plus w is equal to x square plus y square plus z square, then find the Jacobian of u v w with respect to x y z. Now if you look at this relations, so in these relations we are not able to identify that out of u and v and x and y, which are the dependent and which are the independent variables. We are not able to separate them, right? U either as a function of x, y, z, or x, y, z as a function of u, v, w. So these relations are nothing but the implicit relations. So we have to find out this Jacobian by using the formula for implicit function. So if anyone remember the formula for implicit, we have just recited. What is the formula? That if I need to find Jacobian u1, u2, u3 with respect to x1, x2, x3, I have here 3 dependent and 3 independent variables. So in the formula I have minus 1 to the power 3 over here. Clear? After that, what I write? First I need to put these as the functions f1, f2, f3. Look at, first I define the 3 functions f1, f2, f3. How we define these f1, f2, f3? By shifting all the elements on the left hand side, making the right hand side part equal to 0. So this is u cube plus v cube plus w cube minus x minus y minus z equal to 0. Second relation, u square plus v square plus w square minus x cube minus y cube minus z cube equal to 0. Third one, u plus v plus w minus x square minus y square minus z square. So first of all, we define 3 functions f1, f2, f3. So by formula, this is minus 1 to the power 3. Jacobian of f1, f2, f3 with respect to x, y, z in the numerator, divided by Jacobian of f1, f2, f3 with respect to u, v, w in the denominator. This one. Okay. So this is the formula. Now what we need to find? Now we need to find this Jacobian and these Jacobian, these 2 Jacobians. So we start finding these 2 Jacobians over here. Okay. The first one. The first I need to find the Jacobian of f1, f2, f3 with respect to x, y, z. Yeah. Just a minute. So if I look at my relations, they are my relations over here. I start finding the Jacobian of f1, f2, f3 with respect to x, y, z. This one. So by definition, I start writing the definition, the partial derivatives in the first, second and third row. First I start with f1. Take the partial of f1 with respect to x, with respect to y and z and keep it in the first row. So if I start with this, so del f1 by del x, I look at over here is minus 1. Del f1 by del y is again minus 1 and del f1 by del z is minus 1, the first row. For the second row, take the second function f2, take its partial with respect to x, y, z each. So del f2 by del x, if I look at this is minus 3x square, del y it's minus 3y square and del f2 by del z is minus 3z square. This one. Similar with f3, del f3 by del x minus 2x. Del f3 by del y is minus 2y, del f3 by del z is minus 2z. So this is the determinant, means by definition of Jacobian, we are able to write down this determinant. Now we need to solve this determinant. So what we do first, if I able to take something common outside from the 3 rows, so take that common outside. So if you look at in the first row, we take the minus 1 common outside. From the second row, I able to take this minus 3 common outside. From the third row, I able to take this minus 2 common outside, which will give me minus minus plus and minus and 3 to the 6. So minus 6 is somewhere common outside. Giving inside the value as 1, 1, 1. This minus 3 is common, so this will left with x square, y square, z square. And this minus 2 is common, which will left with x, y and z. So this I going to get over here. So look at now the next slide, what we get. So after solving, I have not solved like this. I have taken over here. I have taken the minus 1 common from here and 3 common from here and minus 2 common from here. And I get something like 6 outside the bracket. And we have get 1, 1, 1. We have got x square, y square and z square. And we have got x, y, z over here. And we check out in the last slide what we have outside the bracket. Outside the bracket we have minus 6. Like this. Clear? So I think this minus is left over here. Just a minute. This is something mistake. This should be minus over here. So minus 6 is outside the bracket. Now we start solving it. For solving it, I apply the same transformation. C2 changing to C2 minus C1 and C3 changing to C3 minus C1. I apply the same. Look at. Minus 6 is outside common. C2 minus C1. The column 1 remains same. C2 minus C1 gives me 1 minus 1, 0. Y square minus x square and y minus x. Like this. And C3 minus C1 gives me 1 minus 1, 0, z square minus x square and z minus x. And now you look at that how you solve it. Again we going to take something common outside. So if anyone remember that from the second column, we are taking y minus x common out here. And from the third column, we are taking z minus x common out here. So look at what we get. We left with 1, 0, 0. This is x square. If I take y minus x common, and we know that y square minus x square is y minus x into y plus x. So this will be left with y plus x. Z square minus x, z minus x is common. This left with z plus x. This is x. Y minus x is common. So this is 1. Z minus x is common. So this is 1. So I getting the value 1, 0, 0, x square, y plus x, z plus x and x 1, 1. And now we expand it by the first row. So it's very simple to expand. So when I expand it now over here, I get the value. I solving over here. Look at what we get. This minus 6, y minus x and z minus x is outside, already outside. Expanding by the first row. So this will be 1. This will become y plus x minus z minus x. This one. These two will cancel out, giving you the value minus 6. Minus you can manipulate inside the bracket. So this will become 6, x minus y, y minus z and z minus x. So we get this as our value minus 6, sorry plus 6, x minus y, y minus z and z minus x. So this is the Jacobian of f1, f2, f3 with respect to x, y, z. Next Jacobian, we need to find the Jacobian of f1, f2, f3 with respect to u, v and w. Okay, how we find? Again we have written down our relations. We start finding the Jacobian of f1, f2, f3 with respect to u, v, w. By definition, first I started with this f1. Take its partial with respect to u, v, w, keep it in the first row. Second is f2, take it partial with respect to u, v, w, keep it in the second row. And the third one is this one. Again, I start taking the partial derivatives. Look at del f1 by del u is nothing but 3u square. Del f1 by del v, 3v square. Del f1 by del w is 3w square. Okay. Del f2 by del u, 2u. This is 2v, its partial is 2w. And for del f3, it will become 1, 1, 1. Again, we apply the same transformation, C2 minus C1 and C3 minus C1. Look at what we get. Okay, before applying this transformation, what we take common? From the first row, I can take 3 common outside. From the second row, I take 2 common outside. So what I get? 3 2s are 6 is outside common, and inside I am getting u square, v square, w square, u, v, w, and 1 1 1. Now I apply these transformations. So look at what we get. This is 6. Column 1 remains same. This is u square, u, and 1. C2 minus C1. C2 minus C1 gives me v square minus u square, v minus u, and 1 minus 1 is 0. C3 minus C1 gives me w square minus u square, w minus u, and 1 minus 1 is again 0. Okay. Now what we take again, same, common. From the second column I take v minus u common outside. From the third column I take w minus u common outside, and inside the determinant we left with u square. This is u, v plus u, this will become w plus u, and this is u 1 1 and 1 0 0. And last, similar as the last part, we expanded by the last row. When we expanded by the last row, what we get? Like the same as we have done in the last part. Finally, we get the value minus 6, u minus v, v minus w, and w minus u. Now, both the determinants we have already calculated. Now, we need to find out the final Jacobian. So, these two Jacobian we have calculated in the last slides. So, therefore, the Jacobian of UVW with respect to XYZ by the formula of implicit function, this is minus 1 to the power 3, Jacobian of F1, F2, F3 with respect to XYZ upon F1, F2, F3 with respect to UVW. Just divide these two values, 6 will cancel out, and we left with the value x minus y, y minus z, z minus x divided by u minus v, v minus w, and w. So, this is the final answer for this question. Okay. So, that's how we apply the formula for implicit functions. Okay. Now, the last one more application of over there is called the functional dependence. What is the meaning functional dependence? It says that if UVW are functions of two independent variables x, y, z, not 2, this should be 3. If UVW are functions of 3 independent variables x, y, z, then UVW are independent if Jacobian of UVW with respect to x, y, z is not equal to 0. If they are not, if this Jacobian is not equal to 0, then we say that u, v, and w are independent variables. Otherwise, they are dependent. Otherwise, they are dependent means if for proving that variables are dependent, what we need to show that Jacobian of UVW with respect to x, y, z must be equal to 0. Sorry. So, if your variables are dependent, then you able to find out a relation between them, and that relation is called that these variables are functionally dependent on each other. So, look at how you solve, how you prove that this are functional dependence. Question says that if u equal to x plus y by 1 minus xy and v equal to tan inverse x plus tan inverse y, find the Jacobian of uv with respect to xy and find the relation between them. We know that relation exists only when u and v are dependent upon x and y. And for dependency, what we need to show that this Jacobian must be equal to 0. Then only we say that u and v are dependent variables. Okay. So, we start finding this Jacobian. By definition, I write this is del u by del x, del u by del y, del v by del x, del v by del y. Find all these partial derivatives one by one by taking these values. We apply the quotient rule over here to find out these partial derivatives. To take the partials, del v by del x is nothing but tan inverse x, it's 1 by 1 plus x square. Tan inverse y, it's 1 upon 1 plus y square. Solve this determinant. After solving, we get that this value coming out to be equal to 0. So, means if this Jacobian is 0, means u and v are functionally related relations. Yeah. So, they are functionally related. So, now, if they are functionally related, so there must exist a relation between u and v. So, if now look at what is the relation, Now V here is tan inverse x plus tan inverse y. So this is nothing but tan inverse written as x plus y divided by 1 minus xy. This is the formula for tan inverse A plus tan inverse B. Tan inverse A plus B by 1 minus. And what is this x plus y by 1 minus x? This is nothing but u. So replacing this value with u, so we get that V equal to tan inverse u, and this is the final relation. Look at, or I can say V equal to tan inverse u, or shifting tan inverse to left hand side, we get tan V equal. So this is the final relation between u and V, and this type of relation is possible only when the Jacobian of uv with respect to xy comes out to be equal to 0. Then only we say that u and v are functionally related. Clear? So this is the lecture for the topic Jacobian. Here we have discussed the definition of Jacobian, the properties of Jacobian, two important properties. One topic is to find out the Jacobian of implicit functions, and one is that how you find that u and v, the two dependent variables, are functionally related with each other by finding that Jacobian is 0, and after that we need to find out the relation between u and v. Thank you.